Good morning, afternoon, evening, whenever you happen to be watching this class. Today we're going to go over chapter 2.2, fitting lines to data points. So the first thing we need to discuss, and we've kind of already touched on this a little bit last lecture, but we need to discuss what are first differences. Now, if you see I've got a table here, 2.3, it kind of discusses what first differences are. Our year is our X here. Our retirement plan is our Y. As you can tell, we have a constant increase in our X. We're always going up by 1 here. And if you look at our first differences in our Y, we're constantly going up by 1,950. Okay, that's important. Your first difference is your difference in your Y's as long as your X are constant. If there is a non-constant pattern in your X, say this one would have gone up by 2 instead of 1, then this would have needed to gone up by double of 1950 to keep that same trend, which would have been okay. But most of the time we set it up pretty simple. Just want you to see that you can pick out the first difference. We keep it constant in the X, and as long as you have it constant in the Y, as far as your first differences go, then you're good to go. Essentially, to find that first difference, for instance, on that first one, they just took 42,900 and subtracted 40,950 from it, and that's what gave us that 1,950. And then we checked the difference between the next two and the next two and the next two, and they were all 1,950. Now, if the first differences of the data outputs are constant for uniform inputs, the rate of change is constant, and a linear function, which is important, a linear function can be found that fits the data exactly. If the first differences are nearly constant, a linear function can be found that is an approximate fit for the data. Okay, so ideally we want it to fit it exactly, but not all the time we can have that happen. And as long as we get close, we can find a linear function that approximates the data, and it is probably a pretty good fit for it. So one of the two is hopefully what we come up with. There are instances where obviously it doesn't fit it at all and we can't use one. It's going to happen, but we're looking at those two today. So in the table above, can a linear equation be found to fit, approximately fit, or not fit the data? Well, in that table above that we were looking at initially, we noticed our first differences are exactly the same for our constant increase in our X and our Y here. So because this is exactly the same for every single first difference here, we can find one that is an exact linear fit. So can a linear equation be found to fit, approximately fit, or not fit the data? One can be found to fit it perfectly. All right, let's look at the next example. Example 2.4 gives the projected population in millions of females under the age 18 for projected years from 2020 to 2060. Draw a scatter plot of the data with the X value of each point representing the number of years after 2000 and the Y value representing the population of females under the age of 18 in millions. Okay, so we've got our little plot here, and before we jump over to the calculator, what we're going to want to do here, before we jump over to the calculator, we want to adjust our years because we're talking about years after 2000. That means our initial year here is going to be 20, our next one's going to be 25, 30, 35, 40, this one's going to be a 45, 50, 55, and a 60 year. Okay, now we're going to go into our calculator and we're going to input this entire list. Now I'm going to check real quick, make sure we don't have a B here. We got a B and a C. In our B, it says graph the equation y equals 0.1x plus 36 and the data points on the same axis. Is this a good fit for the data? So we'll also answer that question while we're at the calculator. And C says find the linear equation of best fit for the data using the calculator. So we're going to answer all three of these while we're over there at the calculator. I'm going to show you how to do it right here in front of your face, right? But I also have how to find or how to enter a scatter plot and how to find the best fit line listed right here straight from the book for you in case you need to follow along with that. Sometimes it's easier for people to follow along with it written out than it is to watch it in front of your face, but I'm going to give you both. So let's go over to the calculator real quick. We're going to put in this scatter plot we've got right here, and we're going to put in that line they gave us, see if it's a good fit, and then we're going to find the best fit line on the calculator. So follow me on over there. Alright guys, so we're over here at the calculator. I'm at my little blank screen that we start with. I'm going to hit the stat button and I'm going to go edit and hit enter, and this is how we're going to type in our list. I'm going to clear out my old list, so I'm going to go up to L1, highlight it, hit clear, and then hit enter, and that will clear out the entire list for me. And I'm going to go over to L2 and do the same thing. I'm going to hit clear, enter, and that's going to clear out the stuff in the list. Please do not hit the delete button. If you hit the delete button, it'll delete the entire list, meaning the whole L1 will be gone. You'll have to reset your calculator to get it back. So make sure you clear it the way I indicated that you clear it. Now we're going to type our list in real quick. So the first enter point here was 0. Nope, sorry. We started from 2000, so our first enter point was 20, 25, 30, 35, 40, 45, 50, 55, and 60. Those are all of our years for our X. We entered those in L1. Now we're going to go over to L2 and we're going to enter in the population in millions. So the first one was 37.2, 38, 38.2, 39.2, 39.8, 44, 41, 42, 42.9, and 43.6. Alright, so I have my entire list typed in here. You got to see me type this particular one in. I'm probably, for the rest of the examples that we do for this chapter, I'm not going to type it in. I'm already going to have it typed in when we start the example, just to save some time on the video. If you need to pause the video at any point to type in the list because I'm typing it in too fast or I already had it in there, please make use of the pause button so that you can follow along and do it yourself. Make sure you understand how it's done. Okay. So right now we want to draw the scatter plot. So should be a refresher. We hit second stat plot, and we want to make sure our stat plot is turned on. So I'm going to go to plot 1, hit on, turn it on, make sure my type's listed correctly here. X list is L1, Y list is L2. It should be pretty standard there. Now I'm going to go zoom stat, which is number 9, and I get a beautiful stat plot that looks like this. If you have anything in your Y equals, you're going to want to clear that out, because if you have something in your Y equals, it could draw a random line or a curve across your graph, and that's no good. Otherwise, you should be good to go here. Yours should look pretty much exactly like mine. So we have graphed the scatter plot. Okay. Now they wanted us to input this equation here, 0.1x plus 36, and comment on its fit for this data. Now I'm looking at this, and to me, this does not seem to fit this data at all. This data seems to increase a lot quicker than what this line's increasing. It's not really even that close to very many points at all. I don't think the equation they gave us in part B is a very good fit at all. So what I'm going to do now is I am going to show you on the calculator how to find the best fit line for the data. To do so, we're going to hit the stat button. We're going to scroll right to calc, and we're going to scroll down to number 4. Number 4 is linear regression. L-I-N-R-E-G, and it gives you the form AX plus B. Now, they do have another option for linear regression at number 8, which gives you the form A plus BX. It's essentially the same thing. I like to do number 4 because it puts it in a very standard slope-intercept form. That's typically the one I stick with. If you hit enter on it, it asks you for a few things. It says your X list, and it says L1, which is correct. We put our X's in L1. Our Y list is L2. That's correct. Ask you for the frequency of the list. We usually just leave that blank. I wouldn't mess with that. And it asks you if you want to store your regression equation. Now, you don't have to store your regression equation, but a lot of times if you do, it'll make this next process very, very easy. So what we will do is, in order to store it, we're going to hit vars. We're going to scroll right to yvars, highlight function, hit enter. And we're going to store it in our Y1. You don't have to store it in Y1. You can store it in Y2, Y3, Y4, Y5, Y6, whichever Y you want to. I typically store mine in Y1. Okay, and when I do that, I scroll down to calculate, I hit enter, and it gives me my equation here. It says Y equals AX plus B, where A is 0.155 and B is 34.2777, repeating, and then it rounded that last 7 to an 8. So that is our equation. And I'll go back to our notes and I'll write it down for you so you can see exactly how it's listed out. Essentially, all we're doing is replacing that A with that 0.155 and that B with that 34.27 so that it looks like Y equals 0.155 X plus 34.278, and that is your equation. Now, if you hit Y equals, you'll notice that it stored it right here in your Y equals, and the good part about that is it puts it in exactly for you there. So no rounding that you have to do, and you don't have to convert it and type it in by hand. It puts it in exact for you. If you hit graph, it graphs it for you too. So it stores it, graphs it perfectly for you, and what you can tell is this best fit line here fits a whole lot better than that line they gave us in part B. Okay, does a great job of fitting our data. So let's go back to the notes real quick, write down what we discovered, and then go on to the next problem. All right, so we did the scatter plot for A, so we check that off. We graphed this B part, and it says the graph of the equation Y equals 0.1x plus 36, and the data points on the same axis. Is it a good fit for the data? We determined no, it is not. And then for C, we wanted to find the linear equation for the best fit using the calculator. We found that, and let's see, it was Y equals 0.155x plus, should have written it down. Let me see if I can pull my calculator back up real quick over here on the edge without the video dying on me, and 34.28. So 34.278 so that we keep all the decimals approximated correctly. That was our best fit line from the calculator. Easy enough. Now, like I said, I gave you the written out book example of how to type all this stuff in. It says the best fit line is the line for which the sum of the squares of vertical distances from the data points to the line is a minimum. In order to find the best fit line, we use a process called linear regression, and it kind of gives you a walkthrough of exactly what we did with this exact same example here. Okay, that's pretty nifty and easy. We did it. We're ready to go. We're going to scoot on down to this very next example. This next example says table 2.6 shows the median weekly earnings of women and men in 2013 in dollars. And it does that. It says age, it gives your age, gives women, gives men. Part A says let X represent the earnings for females, let Y represent the earnings for males. Create a scatter plot for the data. So women are our X values, men are our Y values. We want to create a scatter plot for the data. We want to create a linear model that expresses male weekly earnings as a function of female weekly earnings. And we want to graph the linear function and the data points on the same graph and discuss how well the function models the data. So what I'm going to do, I'm going to transition us back to the calculator, and I'm going to go ahead and type this into my list so that when I pull this calculator up, these lists are already going to be typed in. I'll still show you how to get there, but instead of making you sit through here and watch me type one in at a time, if you need to and you want to type it on your own, hit pause, type in your calculator, and then hit play, and you'll be right caught back up with me. See you over at the calculator in just a second. Alright, so we're over at the calculator. Told you I was going to go ahead and type it in. If you need a refresher on how to get there, stat, edit, that's your list. I've already typed the list in. If you need to pause here, type them in to catch up, that's fine. Once you have the list typed in, if you want to just graph the scatter plot, go ahead and clear out that Y equals you had before. If you graph, it's not going to show up. You need to go zoom, stat, every time you put in a new list, and it'll graph it perfectly for you every time for the statistics part. And what we can see here is we have a scatter plot of our data. Now we want to find, because the next question asks to create a linear model that expresses male weekly earnings as a function of female weekly earnings. So we're going to go back to stat, scroll right to calc, scroll down to linear regression, which is number 4, and we're going to basically create a line for this. I'm going to store it in our Y1, hit calculate, and it creates a line for us. Y equals AX plus B, where A is 1.46 and B is negative 140.33 approximately. It stores it in your Y1. It is right there. If I hit graph, look at it. It does a pretty good job of estimating the data. If it doesn't hit a point, it's really near the point, or it splits the difference between the other points. So it doesn't do a bad job given the data that we had. That's that's pretty much it. It's pretty simple, guys. I'm going to go back to the data notes or to the lecture notes. We are going to type in that linear line function, that linear regression that we found. We're going to type it in, so write it down so that you'll have it, and then we're going to kind of move on to the next question. Alrighty, guys, back over here at the lecture notes. We did part A. We're good to go. We did the scatter plot. We need to create the model here. The model that we found was y equals 1.460x minus 140.325. All right, we graphed it just like we were supposed to against the scatter plot, and I think it did a decent job of fitting the data. Now, I mean, obviously it didn't do perfect, had a couple points that were a little away from it, but overall it did not do a bad job at all of fitting that data. So let's go on to the next question. So in the next question it says the total U.S. population for selected years beginning in 1960 and projected to 2050 is shown in table 2.7 with the population given in millions. Okay, so we have our data here from 1960 all the way to 2050. A says align the data to represent the number of years after 1960 and draw a scatter plot of the data. B says create a linear equation that is the best fit for these data where y is in millions and x is the number of years after 1960. Okay, so before we jump over to our calculator, we need to align it to the number of years after 1960. That means 1960 will be year 0, 65 will be 5, 10, 15, 20, 25, 30, 35. This is where you got to be careful because now it's 38. This one is 40. This one is 43. This one is 45. Oof. See? Jump ahead, you can start making mistakes. I'm going to rewrite that 3 as well because it was ugly. So 2025, because we had a jump here between 43 here, the 2003 to the 2025. That 2025 is going to represent year 65. And then that 2050 is going to represent year 90. I want to make sure we get this right. So got all this done here. We're going to create that linear equation that's the best fit for the data. Going to go over and do the scatter plot and everything with it on the calculator. So I will see you over there in just a second. Alright, so we're over here at the calculator. If you need to pause at all and type this in on your own calculator if you hadn't done it already, it'd be a good idea so you can follow along. I have all my data typed in here. Make sure you type everything in correct. If you get it even just a little bit off, it can really mess you up. What I do want to show you here is that in L2, you'll notice that some of the values you typed in will probably be rounded in the viewing window here. That's just because that column for L2 is only so wide, it can only accept so many decimal points. But just because it's rounded where you're looking at it doesn't mean it's rounded in the calculator. If you notice this very last point, I typed it in as 408.695. Calculator rounded it to 408.7 just so it would fit within the window. That true value, that 408.695, is still in there, so don't freak out about that. Don't round the calculator around for you, but don't round initially. Go ahead, type in the full value. That full value will be there. Now, I'm going to go stat, and I'm going to go calc, and we're going to go ahead and calculate the linear regression for this model and do the scatter plot all at the same time. We're going to store this in Y1 just like we've been doing. Gonna hit calculate, calculates it out for me. Y equals ax plus b, where a is 2.607 approximately, and b is 177.195 approximately. It did store in my Y1. I'm good to go there. I need to go zoom stat, which is number 9, and it's gonna zoom it appropriately for me. And what we notice is this line does a really good job of fitting this data. Most of the data points are really, really close to the line, if not on the line. So, calculator did an excellent job. We know what the line is. We'll go back over to the lecture note, write that line down, and then move on to the next example. Alright, so we're back over here. We did the scatter plot, which was A. B, we wanted to find that best fit line, and we did that. It was y equals 2.607 x plus 177.195. And we're good to go with this example. Now, let's look at some of these exercises we've got for this particular lecture. It says, without graphing, determine which of the following data sets are exactly linear, approximately linear, and nonlinear. If we notice on all three of these data sets, our x is set up very nicely. It all just increases by 1. That's nice. I always like to check that. For this particular class, it'll always pretty much be constant. But it's always a good idea to kind of eye check your x. Now let's look at the first differences for our y here. So our first difference here goes from a 5 to an 8. So our first difference there is a 3. Goes from an 8 to 11. First difference there is 3. 11 to 14. First difference there is 3. And 14 to 17. First difference there is 3. Because our first differences here are all the same, this one is going to be exactly linear. Alright. If we look at the next one, it goes from a 2 to a 5, which is 3. Goes from a 5 to a 10, which is 5. Goes from a 10 to a 5, which is a negative 5. And a 5 to a 2, which is a negative 3. Ooh, those aren't constant at all. Those aren't even really close to each other. Negative 5 and positive 5 are actually 10 data points away from each other. Same thing with negative 3 and negative 5, negative 2 data points away. So, I mean, we've got a lot of stuff going on here. To be honest, it looks a little parabolic if you kind of catch how that looks. So this one is non-linear. Let's check this last one. 6 to an 8, that's a jump of 2. 8 to a 12 is a jump of 4. 12 to a 14 is a jump of 2. And 14 to 18 is a jump of 4. So this one, you could probably approximate it with a linear curve or a linear line here. Or a linear function. Because 2 and 4, yeah, they're not exactly the same, but they're honestly not that far off. So we've got differences of 2 and 4 all the way down. So we can probably find one that is approximately linear for this set of data. Alright, so let's see what the next example is. So number 2 says, World IT Cloud Service revenues from 2009 and projected to 2015 are shown in the table. So we have this nice table here. A wants us to create a scatter plot for the data with y equal to the billions of dollars of revenue and x equal to the number of years after 2000. B says to use the scatter plot to determine whether the data can be fit exactly by a linear function. If so, we want to list that function. Okay, so let's get with this. We do need to align for the number of years after 2000. So this will be year 9, 10, 11, 12, 13, 14, and 15. So be sure to do that. I'm going to meet y'all over at the calculator. So if you need to pause here and type in your list so that you can be caught up with me on the calculator, because I'm already going to have the list typed into the calculator when I pull it up. I'll see you over there, and we will do the scatter plot, and we will find that linear approximation. Alright, class, I have my list typed in here, my L1 and my L2, lines up with our stuff. I'm going to go ahead and find the best fit line for it. So we're going to go to linear regression. We're going to store it in our Y1. Good to go there. Hit calculate. It's going to calculate it for us. We'll go back and we'll write this down when we get back to the lecture notes. Y equals 9.18x plus, well, actually a negative 70.57 approximately. If we go zoom stat, it's going to show us our line here. And if we're looking at it, here, we found the best fit line, but it's not an exact fit. To be honest with you, the data kind of looks more like a curve than a line. So maybe a straight line to estimate the data is not the best here. But either way, we calculated it. We're ready to go. Let's go back to the lecture notes, write it down, and move on to the next example. Alright, so we created the scatter plot. We used the scatter plot to determine if the data can be fit by a linear function. If so, list that function. We don't really think that the linear function was the best idea. but we'll go ahead and write down what that linear function was. Honestly, I think a curve would have fit better there. We will be discussing how to approximate curves for data in the future, so be prepared for that. Something we will do fairly soon, but not in this lecture. Now, number 3 says the table below shows the usual dosage for a certain prescription drug that combats bacterial infections for a person's weight, and it gives us the list here. Can the data be modeled by a linear function? Explain. Find the function that models the data exactly. If the model is interpreted continuously, what dosage would be recommended for a 209-pound patient? Now, if we look here at our dosage does increase by 5. So our first differences here, all of them are 5. And you can check all of them if you want to, but they're all 5. If we look at our differences here as well, we're increasing constantly by 11 pounds. And you can check all those as well if you want to. If you go down, they're all 11. So because on both sides here, we're increasing constantly by the same number. So like I said, you can check them all the way down to here. This is 5, this is 5. Can it be modeled exactly by a linear function? Yes. Because the first differences are constant. They're all the same. Okay, so next thing we're going to want to do is go over to our calculator and find the function that models the data exactly. And we'll look at that model after we put it on the calculator, and we will try to figure out what will be recommended for a 209-pound patient. Now, we can honestly go ahead and do that, because if we add 11 to 198, we get 209, right? That would be the next one in the list. And if everything goes up constantly, that should be 95. So hopefully C will turn out to be 95 on the calculator too. If not, we did something wrong. But let's jump over there real quick. We will find the model that fits it. We will make sure we're correct on that 95, and I'll show you how to do that. And we should be good to go for this question. Alright, so we're over at the calculator. I typed both of my lists in. If you need to pause and do so, please go ahead and do that. I'm going to hit Stat Calc and go ahead and run the linear regression on it. If we want to, we can even store it in our Y1 like we've been doing. I try to just make a habit of doing that in case we do need to look at the graph, which we will here. I calculate it out, and we get Y equals 0.4545 repeating plus B, and our B here is 0. So it's a pretty simple equation here. And we'll go back to our lecture notes and write that in a minute. If you do zoom stat, which is number 9, your graph looks like this. I told you I would help you figure out what we would need to type in order to figure out your value for a 209-pound patient on your calculator. In order to do that, we go second calc, value, which is number 1. X is 209. Hit enter, and it says Y is 95 when X is 209. So just what we interpreted to be already on our lecture notes. We are ready to go. So let's go back to the lecture notes and do the next one. Alright, so the function we found here was Y equals 0.45 repeating. It's pretty simple there. If you wanted to write it exactly, we've already kind of found it. Our data is rise over run, right? Our slope is rise over run. We found our rise to be 5, our run to be 11. If you type 5 over 11 in your calculator, it gives you 0.45 repeating. So our function here is just Y equals 5 over 11x, especially because our B was 0. We saw that on our calculator. Pretty simple. All right, and we were correct on part C that it was 95. Well, let's look at number 4. Number 4 says, as the following table shows, projections indicate that the percent of U.S. adults with diabetes could dramatically increase. A says, find a linear model that fits the data in the table with X equal to the number of years after 2010. That's important. And use the model to predict the percent of U.S. adults with diabetes in 2027. Ooh, did a big jump there. And graphically find what year the model predicts the percent to be 31.3. Okay. So before we jump over, there's a couple things we need to do. We need to align our data so that X is equal to the number of years after 2010, which means year 2010 will be 0, this will be 5, 10, 15, 20, 25, 30, 35, and 40. Okay. Also, for part B, when we use the model to predict the percent of U.S. adults with diabetes in 2027, we're not just going to type in 2027. 2027 represents year 17. So we need to know that before we go over to the calculator, make it nice and easy, because we can type in year 17 for our X value and find that. And then I'll show you what to do for that 31.3% and C as well. So meet me over at the calculator. Go ahead, type your list in here. Pause if you need to, and I'll have it typed in for you. We'll find the linear model, and we'll find the answers to B and C as well. All right, class, already got my list typed in here. We're going to find the linear model that fits the data. So we're going to go stat, calc, oops, not one bar stat. Goodness. I'm going to go back to stat now. Had to get out of that. I'm going to go to linear regression. I'm going to store it in my Y1. So vars, Y vars, Y1. Hit calculate. And there it is. Y equals 0.465x plus 16.696. Okay. Now, it's stored in my Y1, which is good. I'm going to do zoom stat so I get a good look at it. There it is. We need to use that model to predict the percent of U.S. adults with diabetes in 2027, which we determined to be year 17. So to do that, I'm going to do second calc, value, x is 17, and it gives me a y value there of 24.594889, which is good to go. If we want to round that, we can say 24.6%. And then C says graphically find what year this model predicts the percent to be 31.1%. Okay, so what we need to do for that, easiest way I know to do that is go back to your y equals here, and we're going to type in 31.1 in our y2. Then we graph it, and what we're going to do is we're going to figure out where they intersect at, and where they intersect at will be our answer. So this line, that line, and then we will scroll over to about where they intersect at, hit enter, and it tells us they intersect at x equals 30.999, y equals 31.1. So basically here in year 31 is when we have that 31.1%. Okay, so let's take the information that we just got, go back to our lecture notes, and write it all out and make sense of it. Alright, so for A, we found the linear model. It was y equals 0.465x plus 16.696 approximately. Use the model to predict the percent of U.S. adults with diabetes in 2027. That was 24.6%. We found that. And graphically find which year the model predicts the percent to be 31.3%. We determined that was year 31, but they don't want year 31 as the answer. They want the actual year for the answer. And since it's year since 2010, we got to add 31 to 2010, and that should give us year 2041. That'll be the answer they want you to input for that one. All right, I think we have one more question, maybe two more questions to this lecture. Got two more questions this lecture. So let's look at the next one. It says the table gives the projections of the population in millions of U.S. residents over age 16 for selected years from 2015 to 2060. And it gives us that in this nice chart. Graph the data with y equal to the population in millions and x equal to the number of years after 2010. So we need to align our data. And we're going to find the linear function that models the data. And we want to know what does the model predict the population will be in 2042? And in what year does the model predict the population will be in 336.827 million? So we will solve all those questions when we go to the calculator. First thing I want to do though is align this data with 2010. So this is going to be a 5, 10, 15, 20, 25, 30, 35, 40, 45, and 50. And also for part C, it wants to know what does the model predict the population will be in 2042. That is actually year 32. So that's be the X value we have to put in for that when we go to the calculator. So I'll see you over at the calculator. Go ahead, pause, type all this data into your calculator because I already have it typed in the calculator when we jump over there. Alright, so I already have the data typed in here. I'm going to go stat calc linear regression to go ahead and calculate what that line will need to be. I am going to store it in my Y1 just like we've been doing. Going to hit calculate. Calculates it for us very nicely. We'll write that down when we go back to the lecture notes. Did store it in my Y1. It's good to go. If you had anything in your Y2, because we had that Y2 in there last time, you might want to delete it out so it doesn't mess you up. We're going to go zoom stat, and it does a really good job here of estimating these points. Next thing we want to do is find what does the model predict the population will be in 2042. And we determined that 2042 represented year 32. So we'll do second calc value for x equals 32. And it gives us an answer of 308.476 million. So we'll write that down when we get back to our lecture notes too. You can go ahead and write it down if you want to. And the last thing we wanted to find is we wanted to find in what year does the model predict the population will be 300. So in Y2 I'm going to put 336.827 million. Okay. So if I graph this, I can see where they intersect. I can do second calc, intersect, and it'll give me my answer. So this line, that line, and I will scroll to approximately where it's at. Hit enter, it finds it exactly for me. And we find out that it's year 47. Okay. Now, we'll have to, when we get back to the lecture notes, we'll convert year 47 to the actual year. I believe it turns out to be like 2057. But we'll do that in just a second. See you back at the lecture notes. Alright, so find the linear function that models the data. We found that to be y equals 1.890x plus 247.994. And for part C, what does the model predict the population will be in year 2042? We determined that was 308.476 million. And it's important to put that million there. D, and what year does the model predict the population will be 336.827 million? We determined that to be year 47, which is concurrent to 2057 because we're talking about years after 2010. So let's move it on for the last example. The table shows the national expenditures for healthcare in billions in the United States for selected years from 1995 with projections to 2020. So we've got our graph here. It says find the linear function that models the data with x equal to the number of years after 1990 and y equal to the expenditures for healthcare in billions of dollars. Okay, so x is the number of years after 1990. Means we have an alignment here. Means that's going to be 5, 10, 15, 20, 25, and 30. And C is going to ask us during what year does the model predict expenditures for healthcare will be 4,659 billion. So let's jump over to our calculator real quick, do some calculations. Alright guys, so we're over here at the calculator, got our two lists typed in. If you need to pause and type your list in, please do so. I'm going to go ahead and hit stat calc, scroll down to linear regression in order to calculate what our line is going to be here. I'm going to go ahead and store it in our Y1. I'm going to scroll down, hit calculate, and it calculates this for us here. We've got y equals 138.22 approximately x plus 97.87. Okay, so I'm going to do zoom stat so that I can see my my line against my curve here. Now we got to answer our other two questions as well. We had the one that wants us to answer what does the model predict the expenditure will be in 2019. That was, I believe, our B question there. 2019 should be year 29, right? Because we're doing years after 1990. So what we will do is we will do second calc value and we'll do it for x equals 29. So we calculate that out, we find a y value of 4,106.16. And to answer that final question, during what year does the model predict the expenditures for healthcare will be 4,690 or 59? What we can do is we can let that value be our y2. So 4,659. We can go and graph that, and wherever they intersect at will be our answer here. Now what you'll notice with this one is after you run your intersect function, or when you try to run your intersect function, you're going to wind up with an error. Okay. The reason we have an error here is because where they intersect at doesn't show up in our graph area here. So what we need to do is we need to zoom out. So we'll zoom out, and now we can clearly see where they intersect at. We'll run the intersect function again, and it should give us our value here. So first curve, second curve, guess, and it tells us they intersect at x equals approximately 33. Okay, year 33 should correspond to 2023, right? Because it's year since 1990. So let's go back over the lecture notes, finish it on out, write it all down. So for B, it was 4,106.16 for the model expenditure in 2019. We do need to write our equation as well here for A. It was y equals 138.217 approximately x plus 97.867. And what did we find for C? We found it to be year 33, which corresponds to 2023. That would be our answer for that one. So we've wrapped the lecture up. That was the last question in it. At this point, you need to go and try your homework for chapter 2.2. Give it a try. If you have any issues at all, please don't hesitate to reach out via email so I can help you out. And after you complete your homework, I guess I will see you again for chapter 2.3.